Okay, welcome all to this Gyan course titled Computational Methods in Fluid Mechanics. It's a pleasure to have Professor E. John Hinch from Cambridge University, who will be delivering most of the lectures. So before I go ahead with the details and the other administrative parts of the course, I would like to introduce him formally. Professor John Hinch is a professor of fluid mechanics in the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge. He's also a fellow of Trinity College and the fellow of Royal Society. His main interests are microhydrodynamics, colloidal dispersions, flow through porous media, polymer rheology, non-Newtonian fluid mechanics, mobile particulate systems, and applications of mathematics to industrial problems. Since 1997, he has been a fellow of the Royal Society and is also a knight of the Ordre National du Mérite of France, a foreign associate of the US National Academy of Engineering, and a fellow of the American Physical Society. He won the prestigious Fluid Dynamics Prize of the APS in 2010. Well, I've known him for close to 2 decades, and I can tell you that there is no one else better suited than him to deliver these set of lectures. And I'm sure that all of you are as excited as I am to listening him to talk on this particular topic. Okay, so John, thank you. A round of applause, hopefully. So now to the course details, I think much of it is on the web. The first thing is we'll hold classes, 2 classes or 2 hours lectures in the morning, one from 9:30 to 10:30 with a break of an hour, and then again we resume it from 11:30 to 12:30. All the classes will be held here in room 240. The room will also be available from 2 to 4 p.m. On all days except Mondays to Thursdays. So if there are some computational assignments or you want to try and program some of the ideas which are there in this course, you can come and do that here. If you have brought your own laptops, nothing better, then you have all the time after the classes to try out these things. I have made arrangements for the access of the computers that are there in front of you. Since we don't need it for another 2 days, maybe in the afternoon or sometime, I'll have a system administrator come and help you out in logging into these machines. So this will come with a common password, a login and a password, and so on and so forth. Now, regarding computer programming, I have circulated a sheet of paper which essentially asks about your experience with computer programming and especially numerical computations. So the idea is to get a feel of what is your experience in terms of numerical computations and computer programming, so that then accordingly we can pitch our problems and go through the material. There will be some assignments during the course which you will need to solve and return them for assessment. The certificates for this course will be given at the end of the course. Now, for any administrative questions, of course I am there, but Ms. Samiksha Yadav, who was there, the lady who was helping you there when you just registered, so she will be there all the time, so you can ask her. But anything else, you can always approach me freely regarding the course. So John, it's up to you.
Okay, this course started about 20 years ago working with my colleague Stephen Cowley, when we realized in my department that nearly all the research students were making computations, and yet we had no graduate course to tell them what the background to making calculations, numerical calculations of fluid flows was. So we started to put together a course. We're not experts in numerical analysis, but we do it. And then we had to learn lots of things, and this course has evolved. So in fact, this version today has got 4 new things that I've not taught in Cambridge before. I learned more things. I expect many of you will go away and do research using numerical methods to solve flow problems, and this course is really the background of what's going on. Often it's a good idea to use some packages, but you might know what they do behind the scenes, and you might want to know about their limitations and better things that you could do. So this is an educational course for people wanting to go on to do research. Fluid mechanics is unfortunately a very wide subject, and that means that there's a wide variety of numerical methods you may have to use. So there's flow past aircraft, there's jet engine noise, The oceans and atmospheres move. Volcanoes have eruptions, which is all fluid mechanics. I'm interested in industrial problems like oil wells, inkjet printing, glass furnaces. They're all fluid mechanics. And each of these different applications of fluid mechanics has got different physics that's important, and it's rather good if the numerical methods you use reflect the particular problems of the physics. So there's a large number of physics equals a large number of numerical approaches which are required to a good approach. A consequence of what I've just said is that I don't believe there's a universal method that solves all possible fluid dynamics problems. So this course is not computational fluid dynamics, which I sometimes call color fluid dynamics. It produces always very pretty pictures, but it's not quite clear what the science and engineering behind it is. So this is computational methods that are used in fluid mechanics, and there isn't a universal method that does all types of fluid mechanics. Actually, in a specialized area like my glass furnaces, there's not a there's not a best method. There's always a first method you use, and if necessary, you can find a better method. You mustn't think there's a best method. You must always be prepared to devise something even better. And this course is sort of the educational background where you might go looking for something better. The course is split into 3 parts. The first 4 lectures are going to take a very simple problem, fluid dynamics problem, with some very simple methods, just to get an answer, to compute a flow. And we'll learn about some of the issues, like how to be accurate. The methods have to be stable and not produce infinities. And there's, in fluid mechanics, a very difficult problem when you come to compute, which is pressure. So when you solve problems theoretically or experimentally, you just had the pressure arrive. Computing flows, you do have to work out why on earth is there pressure and what is its job and where you're going to get it from. So there are some issues which will come up when we look at a very simple problem by simple methods. When we've been through that, there's then a set of 6 lectures on much more complicated, not the simple, but the more complicated versions of, I call it discretization. How do you turn an infinite partial differential equation of fluid mechanics into a finite problem for a computer? And you might use finite differences, finite elements, and all spectral methods, and we'll go through all of those. There's also about time stepping, not the simplest type. What are the difficulties? What are the better versions of time stepping? And then linear algebra, just solving the matrix problem AX equals B. Most computations spend 95% of their time doing just that. So you may want to know more than the simplest methods of solving that problem in order to have a good speed up. And then I've got at the end a collection of special topics. Solving hyperbolic equations on a computer is a bad idea. So there are 2 lectures on what are the problems and some possible solutions. I'm going to talk about free surface problems, fluid mechanics, where the boundary changes. Fast multipoles has a way of solving a Poisson problem faster. There'll be a demonstration of a package of software which you will use. So for exercises for all of you, I hope you will, with something like MATLAB, run all of the codes that I use, all of the problems I solve in this first part, the simplest part. Can you get all my results? That ought to be possible. So we'll start, I think, on Wednesday. And then the second week, we will have had a demonstration of this, a package of finite element software. Then you can perhaps use that to run several cases and do a little mini research project of how do the results depend on varying the parameters in different ways, finding out where your answers are safe and where they become inaccurate and things like that. Okay. So the simple problem, it's a very classical problem, is called the driven cavity. I hope everyone knows what the incompressible Navier-Stokes equations are. Are we all right there? Yeah. They did. I don't think I can teach that from scratch in 5 minutes. So we're going to solve these equations. That's the notation I shall use for incompressibility. And then there is acceleration of the flow due to pressure gradients and due to the diffusion of momentum. And the geometry of this simple problem is a square box. It's in two-dimensional flow only. It's a box which is L by L. That'll be non-dimensionalized to 1 by 1. So it's a square box. And the boundary conditions are on the bottom, no slip. On the side walls, no slip. So there's nothing happening on the sides and the bottom. And the flow only exists because you drive the top plate at a velocity. So the top plate, which is y equals L, from x goes from 0 to L, will be driven at some velocity, and we have to discuss what that will be. Many people take it to be a constant, and they're rather foolish to take a constant, as we shall see. And then we need an answer. We need to get an answer. So the question is, can you please find the force on the top? If I'm going to drag the top plate sideways, what force do I have to apply? So it's a single number. So if you look at a single number, you can ask, is it three-figure accuracy accurate? So before you start writing any code, you might understand what the problem is. It's nice if you understand what the answer is going to be up to a factor of 2. So what's going on in this calculation? You should understand the physics of that. In fact, the other way round is quite good, that when you arrive at a new problem, you've modeled the problem, and you've got some equations you'd like to solve, it's very good to test, do you understand these equations, by how would I write a computer code to solve them? Actually, how do you write a computer code to solve some equations? It actually educates you sometimes on what the physics is going on. So we have to understand the physics, we have to understand the mathematical background, and then we have to understand the numerical methods afterwards. Right. So if we just take one part of the left-hand side of the equation, what is that doing? That's telling you that the information, in fact the velocity, is propagating at a speed u. So in a little time step, it will have moved a certain distance. So information, the velocity is moving, and it moves a distance, delta x, which is given by u delta t. You might, in designing your numerical calculation, want to make the spatial grid smaller than u delta t, so information doesn't jump way down the grid. It only moves a little distance each time, and a little distance is measured by the spatial resolution. Or in other words, you might want to reduce the time step so information doesn't go too fast across the grid. There's then, if we take the left-hand side, the first term on the left-hand side and the furthest term on the right-hand side, there is a diffusion equation. So there's a diffusivity of momentum, which is the kinematic viscosity. That's the dynamic viscosity. And the diffusion equation moves in a time delta t. It moves information a distance delta x, which is the square root of delta t. That means that in very small times, it actually goes quite a long way. But in long times, it's sort of relatively slows down. So again, there's this issue. You might want to reduce the time step so it doesn't go further than one grid block. That actually pushes delta t down to very small. So if you're thinking of this, a spatial resolution of, say, 100 points across a grid, you've suddenly asked typically in non-dimensional times, the time step to be 10 to the minus 4. So information doesn't go. That might not be a clever thing to be wanting. You may want to have a slightly coarser grid so you can have a larger time step. Or you might want to know how to handle that physics a little better. And then one of the really awkward problems is if we look at the acceleration driven by the pressure gradient, the equation there is with the incompressibility condition. What we've done here is really we've got a compressible fluid, but we've set the speed of sound equal to infinity. And so this part of the equations can send information from one side of your experiment to the other side of your experiment in 0 time. We've put the speed of sound equal to infinity. If you push a wall sideways, then the other, and on a tube, if you push the plug, I'm afraid the fluid comes out the other side instantaneously, however long the pipe, if it's incompressible. So this is the first hint that pressure is not a friendly thing for the computing. Okay, so there's a Reynolds number, which I hope you okay on Reynolds number. We'll define it in a minute. There's various things that happen. At low Reynolds numbers, vorticity diffuses very rapidly, and you work in a quasi-static situation. Every instance is in equilibrium. That's difficult for the computer. You have to resolve very fast diffusion of vorticity in a time-dependent calculation. At high Reynolds numbers, there can be thin boundary layers. So you need a high spatial resolution to understand things. So for this simple problem by simple methods, we're going to stick in the middle. And Reynolds number of 10 is the middle. Reynolds number 1 is low. Actually, Reynolds number 10 is quite low. Reynolds number 1 or 200 is high. So in the middle, I'm going to do 10. It's on the low side. But I can't solve it analytically, like 0 Reynolds number. Right, so that's, do you know your physics? Do you know your mathematics? If you've got a set of mathematical equations, what is a sensible question? And a question is not just the equation, but it is the boundary conditions, BC boundary conditions, and the initial conditions. If you have an equation with the wrong boundary conditions, then a solution might not exist. So what is a well-posed problem? You have to supply the right initial conditions and boundary conditions to an equation. So you better understand this mathematics because you're going to do it in a numerical version. So for this first part of the equation, that the left-hand side where we had velocity being propagated with u, that sort of equation is a hyperbolic equation, a first-order hyperbolic equation. It's well posed if you know the function that is being moved around, which I've got here as phi, if you know it everywhere at the initial moment, and if you're working on a boundary, say you start at x equals a and go to x equals b, and the velocity is positive at x equals a, you're going to have to tell me what is coming in, what is inflowing. So you have to tell me the function phi as it comes in over the incoming boundary. It's obvious, but if you didn't tell me that and didn't say anything to the computer about what's coming in, it will invent nonsense. So that's the first order equation. We don't have a second order hyperbolic equation in the in this simple problem we're going to tackle. That equation with 2 time derivative equals 2 space derivatives and a speed of propagation c, that is only well posed, sensible mathematical question if you know the initial data of the function value and you know its initial time derivative, because it's a second order equation in time. And again, at the 2 ends you have to say something. You might want to say the value or its derivative at both ends because you've got information propagating in at both, from both. This equation propagates information in both directions at a velocity c. Okay, Laplace's equation, we're going to end up spending all our time solving this equation. It is well posed if the Poisson equation with a non-zero right-hand side, if the function, if you tell me its value on the boundary or its normal derivative or some mixture between the two. Is that all? Oh, and the diffusion equation. So we do have a diffusion equation in the Navier-Stokes equation, and this is well posed if we know the initial value of the function that's being diffused, and we have to know, because it's second order in space, two space derivatives, we have to know information at both ends, either be told at each end the value or the normal derivative or some mixture of those two. There's some restrictions on that too. Okay, so there are these words, hyperbolic, elliptic, and parabolic, and they come from thinking about this general quadratic equation, and you can that describes a surface in xy, and that surface is either a hyperbola, a parabola, or an ellipse. And if you just translate the coefficients from your partial differential equation up to that and find out what it is, that tells you those funny names, which is not important. Okay, but what is important numerically is that the hyperbolic equations, propagating information along, is very tough numerically. Because if you make a mistake, it will just propagate your mistake. And at the next time step, you make a new mistake, and it will propagate that. And after time one, your solution is swamped by errors that you've picked up. It's a very difficult equation to solve. The elliptic equation, the Poisson equation, is fairly costly. As I said, 95% of computing time is spent solving it in fluid mechanics. The parabolic equation, the diffusion of heat or diffusion of momentum is the safest. You can make mistakes and they just go away by the next time step. It's a beautiful equation to solve numerically. Right. So we're not quite finished about this preliminary thinking about what's going on in our equation we'd like to solve. There is the issue of the velocity that we prescribe along the top. Why don't I want to have a constant velocity on the top? If you have a constant velocity on the top, then near to the corner, the stress, the viscous stresses, the pressure and the viscous stress are inversely proportional to the distance from the corner. And therefore, when you want to integrate the force, the viscous force along the top to find the total force, you're integrating 1 upon x from x equals 0. Doesn't work. True, the computer will give you an answer when you ever ask it a question, but the answer will depend on your spatial resolution. And the more you increase the spatial resolution, the bigger the force gets, because it's trying to be infinity. So you don't do a constant velocity along the top. And in fact, so slightly better would be to say, let's have a linear function, a function that vanishes equally at the two ends, so that sine x vanishes at x equals 0 and pi. Linearly, that unfortunately gives a stress which is logarithmic. It's the pressure that's logarithmic at the ends. And while I can integrate log x from x equals 0, it's not too easy. So it's difficult numerically. It can be persuaded to work, but I'm not going to do that. I'm going for something even safer, because I want to do simple things and show that I get accurate answers. So I'm going to make the velocity vanish quadratically, like x squared at x equals 0 and at x equals pi, x equals L. So when sine x is equal to pi. So I've got a quadratic variation at the two ends. So therefore my stress is order 1 at the ends, and the viscous stress is order 1 all the way along from the two ends, which are potentially singular, but are not now. And so I'm going to get a finite answer for the force. And it won't behave absurdly as I change the spatial resolution. Okay. So that's a sort of, before you solve a problem, you should have a little discussion with yourself about, do you know the physics? Do you know the mathematics? Are there any awkward problems lurking there? Right, so non-dimensionalization. This is a philosophical problem. So engineers, I am quite happy for them to write programs in dimensional units. It's nonsense, but it's all right for engineers. But for scientists, it's totally prohibited. Computers just have numbers. They don't have units of meters and kilograms and seconds. So you have to non-dimensionalize if you're a scientist. If you're a scientist, you're trying to find out the trends of answers. An engineer is going to design one bridge, and if that bridge works, fine. But he doesn't want to understand what bridges generally. Perhaps he does. Okay, so we're going to scale the velocities on the magnitude, the maximum velocity along the top, scale the space x and y by L. It's a square box, so now my box is turning into a box of 1 by 1. And then time, I use this length and this velocity. How long does it take to travel at the maximum velocity to go across the box is the unit of time. And I'm scaling the pressure on the inertial value, rho u squared. There's a viscous scaling that's an alternative, but I want to use, I'm just choosing, it doesn't matter which you choose, the inertial scaling. And then, as I hope you know, there's a Reynolds number which measures the ratio of the inertial terms in the governing equation to the viscous term. The inertial term is u dot grad u, this is rho u dot gradient of u, and the viscous term is mu del squared u. And the ratio of the two is this velocity length divided by the kinematic viscosity, the Reynolds number. And it's going to be 10 for a couple of days. So the non-dimensional equations, not much different. Before we had a rho and a mu, and they've turned into a Reynolds number. That's it. As far as the equations, they've hardly changed. And the boundary conditions have now become on 0 to 1. And x equals 0 or 1, y goes from 0 to 1. So that's the non-dimensional problem, not much changed. And the initial condition, I'm going to start all the calculations from rest. Nothing happens initially. And then we switch on the top moving, and then how does the flow. And I'm mostly interested in the steady state. So there's a solution at Reynolds number of 10, and the force has been non-dimensionalized by, it's a viscous stress, so it's mu u divided by L, integrated along the length, multiplied by L. So the viscous force in 2 dimensions is mu u of dimensions, and then I only have to integrate from 0 to 1 of my non-dimensionalized objects. Okay, I want to find a steady state, and there's a choice of how do you find steady states. So I recommend very strongly you solve an initial value problem. You start a problem from rest or some other condition, and you integrate it in time until it becomes steady. The alternative is to jump in and try and find, just search around for the steady state. The advantage of solving the initial value problem is it's linear. The governing equation is du by dt equals something. So this is a linear question. So it's going for the steady state where you strike out du by dt, you're looking at a nonlinear problem. How do you search nonlinear problems? Difficult. There's also the issue, there might not be a steady state that you're looking for. Your physics may not have a steady state. How are you going to find out if you're only searching for steady state? Your failure to find one is maybe your failure, it may be the problem's failure. There isn't a solution you're looking for, or you don't have a good method for finding it. If you solve the initial value problem, you will find out if there's no steady state, it will go into some oscillation. Well, there might be a steady state, but it might be unstable. You might not be interested in an unstable steady state. So solving the initial value problem will tell you if there's a stable, steady state. There are ways of finding unstable steady states. We get to them later. So near the end of the course, I'll talk about how you might go searching for nonlinear answers. Okay, so one of the problems in solving the initial value problem, starting from rest and hoping you get to a steady state, is it can take a long time to get steady. And there are ways of looking at your solution now and one time, at time 1 and then at time 2, at time 3, looking at those and thinking, am I approaching a steady state? And there are extrapolation methods to find out what is the steady state, rather than having to go all the way out to time 300 before it's steady. So that can be helped. And you don't actually have to start from rest. Sometimes we're interested in, say, the force on this plate as you vary the Reynolds number. Well, if you get a solution at Reynolds number 10, you could then use that steady solution at Reynolds number 10 as the initial condition for searching for Reynolds number 20. And that might be quicker than starting from rest. So there are little tricks around. There's always little tricks. And so one final remark is, many of the techniques for searching for the steady state end up, if you really look at how the method works, are effectively time stepping in some pseudo time. So there's not much difference between the two. We could have some chats at some stage. Okay, pressure. So the idea was that we had this governing equation a minute ago. Where is it? There we are. We have this governing equation, and what we would say is we have the velocity, and this tells me the time derivative. So if I have the velocity at one time step, this will tell me the time derivative, so I can work out the velocity at the next time step. But there's this thing sitting in the way. I need to know that. Where am I going to get that from? Okay. So we'd like to time step from t to t plus delta t, and we can read off du by dt from the momentum equation, except we don't have the pressure. So mathematically, this is not a helpful remark. Mathematically, the pressure is the Lagrange multiplier associated with the constraint that div u is 0. It tells me the mathematical status of this question. So there are techniques which are to live in a world where div u equals 0. So you can design a numerical method. In fact, that's what we're going to do in just a minute. Design a numerical method where div u is automatically 0. It can never be anything but 0. And then the pressure will work out. The other approach is to say, I'm going to time step to the next time, and that velocity probably, while at time equals t, I'd arrange div u equals 0, incompressibility. If I just randomly step forward in time, forgetting about the pressure, then div u is not going to be equal to 0. So then I have to think, what pressure do I have to apply to make sure at the next time step div u equals 0? So that's the second approach, is to somehow constrain the velocity using gradients of pressure. Okay. So the first approach we'll do is we'll have a description of the world which doesn't have div u not 0. I think it's yes. So there are two options. Finding the pressure is called the primitive variable approach, and eliminating the pressure is going to be a stream function vorticity. If I introduce a stream function, then the divergence of velocity is 0 automatically. And then if I take the curl of the momentum equation, I've got a vorticity equation. It doesn't mention the pressure, so I mean, it's fine, nearly. So that's the second approach is the one we're going to do this, this afternoon and tomorrow morning. And then on tomorrow afternoon, we'll do the primitive variable approach. And it's much more difficult. So that's why I'm not doing it first. You'll find that three obvious things. There are three. The obvious thing doesn't work. The next obvious thing doesn't work. And it's only the third, more careful approach handles this. So it is more difficult. Stream function vorticity is... So are we okay on stream function and... Okay, so to automatically satisfy that the divergence of the velocity is 0, you introduce a stream function. I'm using psi. This only works in 2 dimensions, or axisymmetric can be made to work. That it's, again, a sort of 2-dimensional problem. And I'm going to have the horizontal velocity, the x direction velocity, is the y derivative of psi, and the vertical velocity, the y velocity, is minus the x derivative. And then if you take the x derivative of u and add it to the y derivative of v, it's 0. So if you introduce a stream function, you've handled div u equals 0. Right. And something of interest is the vorticity and the curl of, which is the x derivative of the velocity minus the y derivative of the x velocity. That is obviously going to provide me the first term, the x derivative of v is going to be minus 2x derivatives of psi, and the y derivative of the x velocity u is going to be 2y derivatives. So I've got the Laplacian del squared of psi. So the vorticity is minus del squared psi. So we have a Poisson equation, and this afternoon we shall solve that. Not this afternoon, sorry, it's the end of the morning we solve that. Okay. If you take the curl of the momentum equation, you form the vorticity equation of evolution of omega, the vorticity. And the equation in 2 dimensions is a little simpler than in 3. It is that the vorticity is moved with the flow and is not stretched. In 3 dimension, there is another term here, which is omega dot grad u. And that is 0 in a 2-dimensional flow. There's no vortex stretching. The thing that makes hurricanes work and tornadoes and things is vortex stretching, and that's not possible in a 2-dimensional flow. And then we have the diffusion of vorticity. So that's the form of the momentum equation we're going to solve. So, okay, I've just said there's no stretching. That's the 0 on the right-hand side. And then sometimes, but I'm not going to bother, people could have rearranged the second term on the left-hand side, u dot grad omega, the advection of vorticity by the flow. If you substitute everything in, you get the Jacobian of the vorticity and the stream function psi. So that, okay, this is not very useful. If you wanted a steady state and had infinite Reynolds number, then a solution of this would be that the vorticity is a function of the stream function. So that helps some people. It just tells you that the vorticity is constant as it moves around the streamline. So it's interesting physics, but we're not going to use it numerically. So there are 2 boundary conditions. There is a no flux through the... I've got velocity equal to 0 on the bottom and sides, and a horizontal velocity on the top horizontal surface. So there's no velocity through any of the boundaries. There's no efflux from the boundaries. And because all of the... there's no flow out of them, they're all on the same streamline. so that I might as well say the boundary conditions on all of the sides is that the stream function vanishes. This has to be a constant. Why don't we choose the constant to be a nice constant like 0? And then there's boundary condition 2, which is the tangential velocity. This is the normal velocity, the tangential velocity, which is 0 on the sides and the bottom. So on the sides, I want the vertical velocity. Okay. I want the vertical velocity, that's the x derivative, to be 0. And on the bottom, I want the y derivative to vanish. And then on the top, I want the y derivative, that's the u x component, the u velocity, to be sine squared. So, we sort of have a decoupled pair, but it's not quite decoupled. We're going to say that at one time, I know the vorticity. I've just arrived at the new time step, I know the vorticity, so I go away and solve what is the stream function by solving this Poisson problem with a boundary condition that psi equals 0 on the boundary. That's easy. Well, it's not easy, it's time consuming, but that's a nice mathematical question. So we started with the vorticity, we solved this equation, we have the stream function. So at this time, we now have vorticity and stream function. So we would be ready to go to this, knowing this vorticity and stream function at time t, we want to find the vorticity at the next time step by solving this equation. That's that rearrangement we had. But otherwise, it's minus u dot grad omega. And we just, please, can you give me some boundary conditions? Because of two spatial derivatives here, I need a boundary condition on the vorticity, and I don't have one. I have a second condition on the normal derivative of the stream function. So this means this problem is not quite decoupled. But we'll treat it as decoupled, because we know how to solve that, so why don't we do that? And then what we've got to do is we've got to fiddle around and do something a little clever to make sure that we find the vorticity on the boundary condition, knowing this normal derivative of the stream function. So we're going to, the boundary condition is find out what on earth the vorticity is on the boundary so that the normal derivative is right. And that needs quite a bit of thought. Alternatively, if you don't like that, you could substitute this expression for the vorticity into this equation and then solve that, where you have two conditions on psi on the boundary. But that really is nasty to think about. Do you have some questions? Please say so, because... Yes, good.
You said that using a vorticity equation would be better instead of solving the velocity equation directly. So, like converting it to the vorticity equation and then solving. So, commercial softwares, whichever are available, or softwares like OpenFOAM, so they generally don't solve in vorticity form. So, why?
Yes, I have to repeat it. Okay. You're saying that commercial softwares do not use stream function vorticity, but use what I've called here. I'm not the only person calling it. The primitive variables, the original variables, the velocity and the pressure. True, because there's a way of doing that, and in the fourth lecture I'll do that.
Is that the pressure velocity coupling?
Yeah, it's yes, and it's jolly difficult. Okay, particularly when most of the commercial, no. A lot of software packages are in finite elements where there is a really nasty dodge to tackle this problem. Sorry? Okay, fine. Okay, so OpenFOAM, right. That will do what I do, and then later I'll explain when I'm going to work in finite differences. So finite differences are finite volumes, just a conservative form of finite volumes. I'll then talk about finite elements. And when finite elements, so in finite difference, finite volumes if you want, the primitive variables are not easy. And I'll show you two ways of going wrong and one way of going right, which these packages obviously go right, not criticizing. But then when we get to finite elements, you'll find there's yet a worse problem there. Essentially, they can't. There's a worse dodge. There's one of the awkward problems in finite differences pops up in finite elements, but you don't have the cunning way of finite volumes to get out of it. Okay, try another question. Yep. Right, so if they ever try to calculate the force, they're wrong, and you can ignore that bit. If they tell you the value of the stream function in the middle, that could be right, but they have somehow handled infinite stresses. Well, they've not handled them in the corner. But the good thing about the corner is that near the corner there's no motion. Here there's a certain motion, but there's no variation in the motion. So that sort of doesn't give too many options for the flow, other than the stress has gone infinite. So if you're interested in stream function, which is a very smoothed out object, it's going to be right. If you were to ask what is the vorticity everywhere, like in the corner, it would be nonsense. Well, the pressure is needed. So you have this sidewalls, no motion. The top plate's going sideways, so the fluid is going along here. You've got to tell it to go down. And that's done by having a higher pressure in this corner than down there. And that will drive that and it's the incompressible. So when we have fluid going sideways, you know it goes down because you know it's incompressible. So it's got to go somewhere. It can't just evaporate. Yep. No. You'll get values of the pressure which are scaled with rho u squared in the way I do the calculation. So you would find that pressure. I'm doing a non-dimensional calculation, so you have to add the dimensions back in again to go to the particular experiment. And there's really a pressure there. And so as we're going this way, there's a high pressure here to drive it down. Equally, there's a low pressure at this end to suck the things up, to supply the things to go down. Okay, so in this lecture, it's sort of been philosophical remarks. What you should and shouldn't do. We'll get down and do some real calculation very shortly and produce some results. Remember, I'd like you to be able to reproduce these results. So on the questionnaire, you're asked, can you program? And particularly, the easy things to program in that many people use are MATLAB. I actually don't speak MATLAB. And my computer doesn't have, it only has Linux software. So I have a version of that called Octave, which works on simple problems. But there are other things like Python that you might do it in. So are you capable of programming that? But I'll show you some symbolic questions about what you've got to do. Waving my hands, you've got to go across here and do this sort of thing. Hopefully you'll be able to do that during this week. And there'll be some answers, and you've got to show your answers are as good as mine. Okay. Was I going too fast? Probably too slow, because you think you understood it, or you understand much more than I've said. But perhaps I really would like you to pick up a bit of this philosophy of how you ought to do computing if you're going to get it right. Okay.